Hello. Can you guys hear me?
Yes.
Yes? Okay. I can't seem to hear you guys. Okay, let me raise the volume. All right. Okay. So today's lecture will be about the augmented Lagrangian method. Um, and this will be actually very relevant to your next computer assignment number 3. So, but before we get to that, let's just briefly review what we did in lecture 18. So we were talking about duality in lecture 18, and we showed that so the dual problem, if you remember, is the minimization of the Lagrangian essentially over x. Okay, and that gives you a function of the Lagrange parameters lambda and mu. And we showed in lecture 17 that this function is concave in the parameters. Okay, and we also established in lecture 17 that if you maximize the dual function, that provides a lower bound to the minimization for the original optimization problem. But under certain conditions, we have equality here, these two things. So you can actually solve this optimization problem by solving the dual, which is always a concave optimization problem, right? Or convex, I mean, the negative of that is a convex function, so it's a convex optimization problem. Okay, and then the conditions, we called them the Slater conditions, and we went over the proof of that. Okay, and yeah, so it's Slater's conditions. We proved this, proved it under slightly stronger conditions than the general Slater conditions. Okay, and then we looked at the dual of a linear program and, and showed that it was also a linear program, but a slightly different structure. And in your homework, you're actually going to start with this structure and show that its dual will end up with a structure like this. Okay, and then we did an example. Okay, I think that's all we did, right? Last class. Okay. So, any questions about duality? I know on the Piazza there was a question by someone about where we got this form. You get this by just plugging in the x star that we found here. This one, this x star. You just plug it in the expression for Lx mu and simplify. You end up with this expression for d mu. Okay. All right. You'll do another example very similar to this in the homework and verify that duality holds. A strong duality. Okay. So, any questions? All right. No questions. Let's get to today's lecture. So today's lecture is about is actually related to what we talked about earlier in the penalty method, right? So in lecture 17, I think, we talked about the penalty method. Let's see, 17, where was the penalty method? Yeah, so we talked about the penalty method, but to keep the discussion a little bit less complicated for the augmented Lagrangian method, we're going to drop this extra constraint set S. But think that you can always add that back on if you need, especially if you need it to for a function which is not defined on all of Rn. So you have a domain that's smaller than Rn. But all the arguments go through like that. Okay, so we're looking at minimizing this function with equality constraints, right? Hx equal to 0. Okay, and we saw before that we could solve this problem by solving a sequence of unconstrained optimization problems, by adding a penalty. The penalty basically makes this thing large whenever the constraint's violated. And as you let ck go to infinity, you're actually adding a larger and larger penalty for violation. And so eventually, for large ck, the unconstrained problem is going to have a solutions close to the constraint problem. And we showed, in particular, we showed that if we look at the solution to this problem, then every stationary point, you look at the sequence of solutions to these problems as k goes to infinity, then every stationary point that the sequence converges, the solution converges to, is also a solution to the original optimization problem. Okay, so that's what we showed in lecture 17. Now let's see what happens if we apply this method to a specific problem. Okay, suppose we're going to use this as a numerical way to solve this particular optimization problem with the equality constraints. So this is a strictly quadratic function. So Q is positive definite, right? And we have linear constraints, and we'll assume that m is less than n. Okay. All right. So that's the typical setup for with the linear constraints. And in fact, this is the problem that you'll be trying to solve in your third computer assignment, right? Minimizing quadratic with these linear constraints. So suppose you try to solve this problem directly using the penalty method. So let's see what happens. Okay, so let's apply the penalty method. So the unconstrained problem will become x transpose qx plus ck times ax minus b squared. Okay. All right. So actually, this is actually a strictly quadratic function. This guy is also quadratic in x. Okay, but let's see whether it's what form that has. Okay, so let's write down that quadratic, ax minus b squared. Let's expand it out. So that's ax minus b transpose ax minus b. Okay, and this I can expand it as a transpose x transpose x. Sorry, wrong. X transpose A transpose AX. Okay. Oh, what happened there? Huh. I'm not sure what happened there. Okay. Sorry. Strange. Okay. Okay. So is everything visible, or are things frozen or anything? No. All good? Looks good to me. Good. Good. Okay. So this is minus 2 x transpose A transpose B for the linear term, and then you have B transpose B from the last term, right? But if you look at this quadratic function, this is a quadratic function, right? If we look at this term here, this matrix that defines the quadratic, what kind of matrix is it? Okay, is it positive definite or positive semi-definite or what? Anyone?
It's positive definite and
it's
symmetric.
Positive definite. In fact, actually, it cannot. It's only positive semi-definite. It can't be positive definite. And the reason why it can't be positive definite is because I'm assuming that m is less than m. Okay, since m is less than n, so this is a symmetric matrix. It's a square of a matrix, so it has to be positive semi-definite, and easily verified by just verifying that x transpose ax is always going to be greater than or equal to 0 for all x. Okay, because it's a square of something. But because the m is less than n, if you look at the rank of A transpose A, that has to be less than or equal to m, which is less than n. So you have an n by n matrix with rank less than, strictly less than n. So it cannot, its determinant has to be 0. That means its minimum eigenvalue has to be 0. Everyone see that? So it cannot be positive definite. It can only be positive semi-definite. Okay, it has to have a minimum eigenvalue of 0. So this could be a problem when you're trying to solve this optimization problem. Okay, this unconstrained optimization problem. This guy is okay, but this guy is a quadratic that could have it could be so-called ill-conditioned. And so what happens when you have an ill-conditioned thing? So let's examine it a little more closely by trying to minimize this. So we're going to minimize this function. Let's call that function the penalty version of the optimization problem, unconstrained optimization problem. I've rewritten in this form with CK included there. So this is the same as minimizing this quadratic xq plus CK A transpose A x minus 2CK x transpose A transpose B plus CK B transpose B. So now if you look at this matrix here, Q is positive definite, CKs are positive, A transpose A is positive semi-definite. So this whole matrix is going to be positive definite. So Q plus CK A transpose A, this whole matrix, this one is positive definite. You can add a positive definite matrix and a positive semi-definite matrix, so you'll get a positive definite matrix. So this optimization problem, which I call PK, is a strictly convex optimization problem. Right? So the solution can be obtained for a convex optimization problem. How do you obtain the solution? Yeah, this is unconstrained. So how do you obtain the solution?
Gradient.
Just set the gradient equal to 0. It's strict, so it's going to be unique too. Okay, and so if you set the gradient equal to 0, you get that Q plus CK A transpose A times X. There's a 2 there, but we can get rid of the 2 from the middle term. So 2 times CK A transpose B. So that 2 goes away because I got rid of it from the first term. This is equal to 0. And you can solve for this as xk equals Q plus CK A transpose A inverse CK A transpose B. And what I'll do is I'll take the CK and take it inside here. If I take it inside there, I have to divide everything here by CK. So this is equal to Q divided by CK plus A transpose A inverse A transpose B. So that's the solution for xk, the unique solution. Okay, so far it looks good. So suppose now we apply gradient descent to solve this optimization problem. So for every fixed CK, this is a strictly convex function. So it'll have a condition number that's something finite. Okay, right? So what's a condition number for this? For if you try to optimize this. Okay, you're going to have linear convergence, right? You're just using straightforward gradient descent, you'll have linear convergence. And you can, the condition number for this is going to be this. Lambda max of that matrix divided by the lambda min of this matrix. We saw that before for quadratic function. Okay. But what happens as k goes to infinity? I should just say, I should really be saying as k goes to infinity, ck goes to infinity. And what happens to lambda min of this?
Goes to 0.
So this is becoming the lambda min of A transpose A. Okay, which is 0. Right, so the problem becomes ill-conditioned as k goes to infinity, because the condition number goes to infinity. Okay, so you're going to run into some numerical issues as you make C large. So then you may take a long time to converge to xk and x superscript k here in iteration k of this, and so then it'll, you might be getting closer to the optimum solution of the constraint optimization problem, but your optimization will be really slow, right? Okay, so how do you get around this and come up with a numerical method that doesn't suffer from this problem? And the main problem is that you really have to let ck go to infinity in order to get a solution to the original optimization problem. So can we avoid that somehow? And that's where the augmented Lagrangian method comes in. So what's the augmented Lagrangian method? So you start with the penalty, but in addition to adding the penalty, the quadratic penalty, you also add in the Lagrangian, lambda transpose H. That's why it's called the augmented Lagrangian. Okay, and of course, with here, lambda is some vector in Rm, and C is positive. Okay, so and now let's look at xk, which is minimizing this augmented Lagrangian with C replaced by ck. Lambda is something fixed. Okay, and we can still let ck be positive and go to plus infinity, and k as k goes to infinity. This up arrow means that ck goes monotonically up to plus infinity as k goes to infinity. Okay. Then we know. Then what we can show is that this adding this guy here doesn't make a difference. So remember, let's go back to lecture 17. We showed in lecture 17 that for the penalty method, that every limit point x bar is a global min of pu, right? So, and we don't have the s to worry about here in this discussion. So our s is all of Rn, so it's closed, obviously. So we don't have to worry about that. So it turns out that adding this guy here doesn't really make a change to the proof. Every limit point of this xk with this additional term in there still satisfies the condition that it's going to be a global min for P. And you're going to show this. It's very easy to show based on the same steps as in lecture 17. And you're going to show this in homework 5, which will be out today, by the way. Then what's the advantage of adding this term? Because, if you're going to let ck go to infinity in order to get the limit point be a global min of p, then you got that already without having this thing. So what's the advantage of adding this thing? The advantage of adding this thing is that if this lambda can be chosen close to the Lagrangian parameter corresponding to the optimum, okay? So what's that mean? So this is actually a pretty technical result that's given in your textbook, which I'm not going to actually prove because it's kind of a little bit beside. Yeah, it's a detail that I didn't think I should spend the time working on in this course at least. But you can read it in the book if you like. So what does this result say? So this is in section 4.2.1 of the text. It says that if x star and lambda star satisfy the second order sufficiency condition for x star being a strict local minimum for p, right? So that's a second order sufficient condition in terms of the Lagrangian, right? So you look at the Hessian of the Lagrangian function and make sure that x transpose or y transpose the Hessian times y is strictly positive for x belonging to v star, y belonging to v star, v of x star. So that's the second order sufficiency condition. So suppose that x star and lambda star satisfy those conditions, then you can show that as long as c is bigger than some threshold c bar, it doesn't have to go to infinity. There should just be above some threshold c bar. Then you can show that there exists a gamma positive and an epsilon positive, such that if I look at the augmented Lagrangian function, okay, for any value of x, it's lower bounded, and lambda star, it's lower bounded by the augmented Lagrangian function at x star, lambda star, plus this this term, x minus x star squared times gamma. For all x that's in an epsilon ball around x star. So what does this mean? So if I'm adding something positive and I'm still getting, and the sum is still less than this, that means that x star is a, what does it say about x star? In every neighborhood.
Local
Yeah?
Local min?
Yes, yeah. I can't seem to hear you, but I think you said local min. Yeah. It's actually a strict local min of the augmented Lagrangian. So what does this mean? So if C is larger than some threshold, I can restrict my search so basically this is saying that if X star is a minimum, a strict local minimum of the original problem, then it's also going to be a strict local minimum for this augmented Lagrangian, which is unconstrained. Okay, as long as C is bigger than some C bar. So I can restrict the search for minima of P to the minima of this augmented Lagrangian. Right? As long as I'm operating at lambda star. So somehow if you can magically choose lambda to be close to lambda star, okay, you may not, but you don't know what lambda star is beforehand, then the augmented Lagrangian method can work without having to make ck go to infinity. So ck bigger than the c bar is enough. Okay. let's do an example, and then I will talk about how we might be able to choose lambda close to lambda star without actually solving. Of course, if you solve the original constraint optimization problem, then you would know what lambda star is. But then you wouldn't need the augmented Lagrangian method anyway. So that's not the point of this method, right? So somehow you should be able to come up with a numerical way to make lambda close to lambda star in the iterations for the augmented Lagrangian method. Okay, so that's but let's do an example first of why, to illustrate that if you choose lambda close to lambda star, you don't have to make C go to infinity. Okay, so very simple optimization problem. Okay, so I'm minimizing this quadratic subject to the equality constraint x1 equal to 1. And you can easily see that if you're constraining x1 equal to 1, then the minimum of this happens at the x star is going to be 1 and 0 for the second term. And lambda star has to be -1. That just comes from taking the gradient of the Lagrangian and setting it equal to 0. So this is very easy to solve. You can do it at home if you want, just to confirm. But 1, 0 is the optimum x star, and -1 is the lambda star. So now let's examine how the augmented Lagrangian behaves as when lambda is close to lambda star. Okay. So the augmented Lagrangian is the function plus lambda times constraint plus. And now C, I'm just going to put a C over 2 just for convenience. So scaling it doesn't really matter. You can define that as C prime if you want, or a C tilde or something else. But so this is so that when I take the derivatives, I don't have to worry about a factor of 2. So okay. So this function is strictly convex in X, right? Again, you can easily see that by looking at the Hessian. The Hessian of this guy is the identity matrix. And what about the Hessian of this guy? Well, this is just going to be 1, 0. And so you add that to the identity and still remain a positive definite matrix. So this is strictly convex in X. So let's look at the gradient. The gradient is 0. Will give me the minimizer. So setting the gradient to 0 will give me the minimizer. So let's set the gradient equal to 0 and solve. And it's not that hard to see here that setting the gradient equal to 0 will, first of all, x2 has to be 0 because x2 only appears in this term. So 2x2 equals 0 will give me x2 equals 0 here. And x1 can be obtained by taking the derivative with respect to x1 and setting it equal to 0. So you get x1 plus lambda and then C times x1 here. So when you do that, when you combine all those things, you get that x1 should equal C minus lambda divided by lambda plus 1, divided by C plus 1, sorry. Now, if you look at any C that's positive and let lambda approach lambda star, right? So in the limit, as lambda goes to lambda star, remember lambda star is -1 here. So as lambda goes to -1, this becomes C plus 1 divided by C plus 1, which is equal to 1. And of course, x2 is always 0, so that's just 0. So as long as C is actually, in this case, the threshold C bar is just 0. As long as C is bigger than 0, you're guaranteed that as you approach lambda star, any fixed value of C that's positive, x of lambda C will go to x star. And of course, just to verify that, no matter how you choose your lambda, if you let C go to infinity, you will get the solution. We already, you're going to prove that in homework 5, but it's very similar to what we did in lecture 17 for the penalty method. So for fixed lambda, as you let C go to infinity, what happens here, as C goes to infinity, this ratio just becomes 1. Right? And so the limit of x is again x star. Okay, but this is not as interesting. This result is not as interesting. What's more interesting is this, that if you can choose your lambda close to lambda star, then C doesn't have to go to infinity in order for the minimizer of the augmented Lagrangian to be close to x star or equal x star. Okay, so let's repeat that. So if lambda can be chosen close to x star, then we can avoid ill conditioning that might occur as Ck goes to infinity in the penalty method. Okay, so going back to this problem here, so we, as long as Ck is bigger than some threshold, C bar, right? You're going to get if you can choose if you add the if you augment this optimization problem with a lambda lambda transpose x, then you don't have to take, and if you can somehow make lambda close to lambda star, then you don't have to make C super large. Okay, you will get a solution close to, you may have to increase C a little bit, but you don't have to make it go all the way to infinity. You'll get a solution that's getting close to the optimum solution well before that happens. Okay, so is this clear? Okay, so I tried to take material that was spread over 2 chapters in your textbook, a lot of material, and condense it into one lecture, just to give you the high level ideas. But if you want the gory details of the proofs of some of these results, that gets really messy. And if you try and read the book, you can do it, but without this this summary, it would have been even more confusing, I think, for you guys. So my goal was to just at least give you the high level ideas of why this augmented Lagrangian method works, and then we're going to apply it in your computer assignment 3 to get even more intuition for why this works. Okay, but do you have any questions? Because we'll take a short break soon before I tell you how to choose lambda close to lambda star without knowing lambda star. Questions? Don't feel shy. No?
Could you
Either
just go
everything's
over?
clear or everything is really confusing.
I think I got lost after you said we established that the Lagrangian of x star, lambda star, mu star is local min. So if you could go over again why we want a lambda close to lambda star.
Oh, yeah. So if we fix lambda to lambda star and then look at the augmented Lagrangian, right? Then if x star is a strict local min for P, then it's also a strict local min for the augmented Lagrangian. So if I'm now looking for a strict, searching for a local min for P, okay, I know that if it's a local min, any local min for P will also be a local min for the augmented Lagrangian, as long as C is bigger than some threshold. So I can then look at the, restrict my search to local minima of the augmented Lagrangian. Right?
That makes more sense now.
Can you go to page 2? Excuse me.
Mm-hmm. This one?
So yeah, so is there a CK square missing on the, like, above PK, the line, the first line?
No, it's not square. It's not
I mean,
square.
XK equals,
Yeah, so this one, it's not square, right? Because the CK is not taken.
oh no, not this line. The most bottom one.
Which one? The bottom, this one?
Yes. Is there a CK square missing here?
No, I'm just taking the CK and bringing it down here. There will be an inverse, right?
Oh, it's inverse. Okay, I see.
So this will go inverse. So that'll get
Okay.
CK, and then this will divide.
Okay, thank you.
I didn't have to do that. I mean, I could have left it in this form and just said, as CK goes to infinity, this dominates and this goes away. But I thought I would leave it. I thought I would do this because then there's a CK here and a CK here, and you wonder what happens, with this guy outside. Just to convince you that this guy was not going to affect anything, I brought it in. Okay. Any other questions? All right, so let's take a short break and we'll reconvene at 11:40. Okay. All right, so let's that's good. Let's get to the So the thing is, so if lambda can be chosen close to lambda star, then things are nice. So how do we make lambda close to lambda star without knowing lambda star beforehand? So that's where duality comes to the rescue. So probably say that. We'll use duality. So how do we use duality? So let's look at our original optimization problem. We want to minimize fx such that hx equal to 0. Okay, and the Lagrangian for this thing, this is not the augmented Lagrange, it's just the plain old Lagrangian. So that's given by this expression here, right? And the dual we know is the minimum of this Lagrangian over x. So that gives you a function of lambda. This is a concave function. So let x lambda be a minimizer of this L x lambda. Then we know, assuming of course differentiability and so on, that it satisfies the gradient condition, that the gradient has to equal 0. Okay, I purposely wrote out this lambda transpose hx as the summation of lambda I hi, and then I could just write the gradient of this. You could also write it in matrix form, like we saw in some earlier lecture when we were talking about the Lagrange multiplier theorem. I thought it would be a little less confusing just writing it in terms of the gradients of the hi, right? Yeah, so this guy is just summation lambda I. Okay, so if x lambda is a minimizer, then d lambda is f of x lambda plus summation I equal to 1 to m. Now let's assume that for now that d lambda is also continuously, it's concave, but not necessarily going to be differentiable. We have to actually prove that separately. Let's assume this is concave and continuously differentiable. All right, but sorry, it's already, we know that it's concave. Just assume that it's continuously differentiable. So assume, and this is actually an important point, because we'll see next week that we can actually handle cases if you have a convex function or concave function. Okay, it's not that big of a deal if the function is actually not differentiable. You can generalize the notion of a derivative or a gradient and define something called a subgradient, okay, that plays the same role as the gradient, except the subgradient is not going to just take on one value necessarily. Okay, so that's I can't talk about that right now, but just note, and I'll remind you of this when we get to subgradients next week, that we don't really need d lambda to actually be differentiable. But suppose d lambda is differentiable, then I can find its derivative using this expression. So or its gradient using this expression. So let's take the partial derivative with respect to the ith component of lambda. Okay, so in order to compute the partial with respect to the ith component, I need the partial of this guy. I need the partial of this guy with respect to the ith component, and I need the partial of this summation with respect to the ith component. So let's compute that partial of f first. Okay, so if I compute the partial of f, what I get is is that, what do I get? So I need to write this as a, so this, again, the chain rule, right? So the chain rule, so I take the partial of f with respect to the x, with respect to each component of x first. So I take the partial with respect to, say, xj of f evaluated at x lambda. Okay. And then I have to take the partial of xj lambda with respect to d lambda I, and then sum this from j equal to 1 to n. Okay. Because there are n components in x, and I basically have to take the derivative with respect to lambda I of each of those components. And so that's how I get this summation. This is similar to what we did when we talked about backpropagation for neural networks, right? So we saw this step before. So I can write this as a dot product of two vectors, right? Put all these guys, all these partials, x1 through xn lambda with respect to lambda I into a vector, okay? And then multiply that by the gradient with respect to x of f of x lambda. So compute the gradient of f with respect to x, substitute x lambda inside, and you get this gradient vector. Take the dot product of that with this vector. Okay, so I could take all these. This is a row vector. I could take each of these rows and make a matrix out of it. So I'm going to form a matrix by looking at by taking as the first row this thing with I equal to 1 and so on and so forth. You get m rows. So I'll call that matrix the gradient matrix of x lambda. So this is x lambda 1, x n lambda 1, and then all the way to xm x1 lambda m, xn lambda m. Okay, so put all these guys into a matrix, and this is basically an m by n matrix. Okay, so if you did that, then if I take all of these partials and put them into a vector, that vector can be formed by taking this matrix and multiplying it by this gradient vector. So I'll get each of the components of the gradient vector. So the gradient with respect to lambda of f of x lambda is given by the gradient of this gradient matrix x lambda times the gradient with respect to x of f of x lambda. Okay, seems a little bit complicated, but it's actually not. It's just an application of chain rule. Okay, so you get, that's how you compute the gradient of f. Similarly, you can compute the gradient of each of the HIs, same procedure, gradient with respect to lambda of x lambda times gradient with respect to x of HI x lambda. All right, so then using the fact that d lambda is the sum of these two things, I get that the gradient of d lambda with respect to lambda is the gradient of this plus the gradient of this. Okay, so it's a gradient of respect to lambda of f of x of lambda plus the gradient with respect to lambda of the summation Okay. Now, the gradient with respect to lambda of f of x lambda we got here. And the gradient of each of these components we also computed. But when you take the gradient with respect to lambda of this summation, you have to break it up into two parts. One, you take the gradient with respect to this lambda vector that's multiplying here, fixing this guy. So that'll just give me an the vector h of x of lambda. And then I take the gradient with respect to the other components using this formula. So let's go ahead and do that. So if I did that, I get from the previous result, this gradient is just the gradient matrix times the gradient of f. And if I look at each term inside the summation, fixing this lambda first, I'll get the gradient of the hi, which is the gradient matrix x times the gradient of hi. Okay, and then what's missing? What's missing is that when you fix the hi of x lambda and then take the gradient with respect to this coefficients vector lambda. So what do you get then? Anyone? What's the last term?
H of x lambda.
Just h of x lambda, very good. It's just the vector h of x lambda. And so I can then simplify this a little bit. This matrix is common to these first two terms. So I'll take that matrix out and then I'll get the gradient of this plus the gradient of this. Okay. All right. And then plus h of x lambda. Okay, but if you look at this guy inside here, let's go back to the previous equation here. This is 0, right? Because x lambda is a minimizer value. The gradient condition says that it's 0. This is 0. So you plug that in and you get that this is 0. So all that stuff we wrote about this matrix x lambda really didn't matter at the end. And to compute the gradient of d lambda, this just becomes 0. All you're left with is just h of x lambda. Get this nice result. And interestingly, this holds even when d is not differentiable. And that's what you're going to see in homework. That's actually one of the problems in homework 5, when we use the notion of subgradient to show that this kind of result holds even when d is not differentiable. In fact, using the subgradient approach, you could prove this result much more easily. Actually, it turns out to be just a few lines, 2 or 3 lines. You completely avoid this matrix, gradient matrix x lambda. And you'll see that when you do the homework. Okay, but the end result is what's interesting, that the gradient is h of x lambda. Now, d lambda is concave. We know it's concave. The dual is always concave and lambda. So we can use gradient ascent to find lambda star. In fact, we can actually do this even when the gradients don't exist. You can use subgradients. Okay, so we'll see that next week. But what's gradient descent? It's basically the gradient descent with the sign change on the gradient, right? So if we want to climb along the gradient instead of going down along the gradient, your gradient iteration will look like this. So lambda k plus 1 is lambda k plus some alpha k positive times the gradient. Instead of negative, you have positive. Okay, but alpha k is some positive. All right, and well, that can be written as lambda k plus alpha k times h of x of lambda k. Okay. So a gradient descent can be performed just using h at the x value. Okay. And it turns out that this gradient descent remains the same even when I add a quadratic penalty. Okay. So it's a little bit complicated, more complicated to show that, but basically you get the same form even with a quadratic penalty added to it. Which means that I can use this gradient descent to try and get close to lambda star. All right. So this whole thing leads to what's called the method of multipliers, which is a numerical technique to solve equality constraint optimization problems. So the method of multipliers says that what you need to do at time k, a step times step k, is find the minimum of LCK So at time k, you have lambda from a previous iterate. I'll call that lambda k. Okay, and you look at the augmented Lagrangian with lambda k and some choice for ck, right, at time k. Again, you will take an increasing sequence of ck's. Okay, and then to update your lambda for the next time step, you don't fix lambda, you update your lambda, because your goal is to try and as k progresses, you'd like your lambda to get close to lambda star. So that's where you use the idea of this idea of gradient descent with ck. Now here's a little catch here. So this is the confusing part. What you end up doing is using a step size. This is actually an increasing step size, right? As ck is increasing. Okay, you're using an increasing step size to do gradient descent. Okay, so it seems a little counterintuitive that this should work, but it turns out that actually this gradient descent actually does work. Okay, and that's because actually you can show that as the optimization proceeds, that this ck satisfies the conditions required. So remember, for gradient descent with constant step size, you needed some condition based on Lipschitzness, right? But you can show that something like that actually does hold, even though you're increasing ck in this case. Okay, so it's a little bit beyond the scope of this class to get into those details, but what you can essentially show is that the method of multipliers, this algorithm, where at each time k you minimize the augmented Lagrangian and update your lambda this way. This does converge to a minimum of p under certain conditions. What are those conditions? Those conditions actually turn out to be the same conditions that we stated here. So basically, if the x star and lambda star satisfy the second order sufficient condition for x star being a strict local minimum for t. Now, in practice, how would you verify something like that? So if for example, the original function is convex, okay, then the augmented Lagrangian is also going to be convex, right? We have only equality constraints, so augmented Lagrangian is going to be if we have a convex optimization problem with linear equality constraints, then the augmented Lagrangian is going to be convex, and so the second order sufficient conditions will be satisfied because it's a convex function. L is a convex function, and so that's one example under which the conditions required for the convergence of this will be satisfied. And that's kind of example that you'll be looking at in your computer assignment 3. Okay. But there are, more, detailed conditions given in your textbook. So you can, if you're interested in those details, look them up in the textbook. But there are certain conditions you can show that this algorithm will converge as to x star as k goes to infinity, at least to a local minimum of the original optimization problem, x star as k goes to infinity, without having to take ck to infinity. So it'll turn out that as long as ck is large enough, and in practice, how would you make ck large enough? What you do is essentially come up with a way to slowly increase ck, and then you use as a stopping criterion as something based on the minimum of this optimization problem not changing very much. Okay, so that's a practical way to do it. Okay, and that's what you'll explore in your computer assignment 3. Again, this is really a numerical technique, right? So and you can give it some theoretical justification. Okay. So this is what you'll be exploring in computer assignment 3. But let me give you a simple example to illustrate that this kind of thing can actually work. So let's look at the case where we have linear equality constraint, very, very special case that we just studied earlier. We have a convex function, linear equality constraint. Okay, we know the solution is x star is 1, 0, and lambda star is -1. Okay, so let's apply the method of multipliers to this. Okay, so if we solve this, we already actually solved this optimization problem earlier. We know that xk is ck minus lambda, let's call it lambda k here, divided by ck plus 1, and the second component is always 0. But what about the Lagrangian update? Sorry, Lagrangian parameter update, so lambda update. So this is or our gradient ascent. So gradient ascent step will use lambda k plus ck times h evaluated at xk. So I need h evaluated at xk here. So h is just x1 minus 1. So it'll just be ck plus ck minus lambda k divided by ck plus 1 minus 1. This is x1 minus 1, right? x1k minus 1. Okay, and so if we simplify this, this becomes lambda k divided by ck plus 1 minus ck divided by ck. Okay, so now let's see whether this gradient ascent iteration actually converges to lambda star, right? So to see that, let's look at the difference between lambda k plus 1 and lambda star. We already know lambda star is -1 in this case. So lambda k plus 1 minus lambda star is just lambda k plus 1 plus 1. Lambda star is -1. And so now we plug in lambda k divided by ck plus 1 minus ck over ck plus 1 plus 1. And if you simplify this, you get lambda k plus 1 divided by ck plus 1, right? Which is lambda k minus lambda star divided by ck plus 1. All right, so now let's see this. So what's happening here? I can write, so this is, I can write it slightly differently. So I can write this as 1 over ck plus 1 times lambda k minus lambda star. So now suppose I make my ck larger than some positive threshold. It can be anything actually, any positive threshold, c bar. Take any c bar positive. As long as ck is bigger than c bar for all k, then this coefficient is less than 1. Right? So this coefficient, this will become, this is less than 1 over c bar plus 1, which is strictly less than 1, because c bar is positive. So what does that say about lambda k converging to lambda star? Go back and think about what we did when we looked at convergence of with strong convexity, right? We had a similar form. So what's going to happen to lambda k? First of all, lambda k has to go to lambda star as k goes to infinity. But how does it go to lambda star? So it's a geometric convergence, right? Because this coefficient multiplying here is less than 1. So geometric convergence. So it's basically what we call linear convergence. Okay. So lambda k basically converges to lambda star. And since lambda k converges to lambda star, xk converges to 1, 0. Why? Because xk is given by this expression here. And this guy is going to 1, and this guy is basically, sorry, this guy is going to lambda star, which is minus 1, so this ratio is going to 1. Now, you don't have to make ck go to infinity in order to have lambda k go to lambda star linearly. But in fact, if you make ck go to infinity, then what happens? Then this convergence of lambda k to lambda star is going to be faster than linear. Right? So it's going to be some form of superlinear convergence. But in practice, we don't want to do that because we don't want ck to go to infinity, because that might lead to problems with this optimization, right? The optimization to find xk, right? And we saw that in this example. Right? We have ill conditioning when you're trying to solve xk. So we don't care that lambda k goes to lambda star superlinearly so much as we care about this xk optimization being ill conditioned, right? So in practice, what you do is you would increase ck, and by the way, there are some guidelines on how to do this in the textbook, and I refer you to those guidelines. Actually, I'll probably just give you those guidelines in your computer assignment, and you can use those to play around and to figure out ways to increase your ck, so that you would avoid ill conditioning and still get a solution that's close to X star. Okay. confusing, or at least some of it made sense?
The example helped.
Okay. All right.
I have a question on lambda being close to lambda star.
Yeah.
So I think the equation on the previous slides shows that when lambda equals lambda star, then we have that inequality.
Yeah.
But what if lambda is not equal? It's just being close. How can we show like the x star?
Yeah. So this is just intuition, right? For it, it's not a proof. And when lambda is close to lambda star, you're not saying that that the solution that you find through minimizing the augmented Lagrangian is going to be close to x star. It may not happen in practice, but what you can show, though, separately through an argument, is that this iteration works, where that this method of multiply works. This thing works. Okay, you can prove separately that this will actually, under certain conditions, of course, on the function and the constraints, you can show that this iterative procedure will converge to a local minimum of your original optimization problem.
Okay, so lambda goes to lambda star and x goes to x star is sort of a coupled.
A coupled way. Yeah.
Okay.
Yeah.
Exactly.
Yeah. But rather than going through to gory details of that proof, I thought I'd just give you some intuition here as to why this method of multipliers might work in practice. Okay, but if you want to see the details, look at the textbook. But it is a little bit confusing. I don't think that material was written that well by the author. So it's also like in different places. Some of it is in chapter 4, some of it in chapter 5, and then he goes back and forth. And so it's a little bit confusing. Okay, and there's also the original paper by Nosadal and Wright. I think it was sometime in the 1990s on the method of multipliers. So you can search for that on the on Google Scholar, and then maybe reading that paper will give you a little more insight as well.
Yeah, thanks for the reference.
All right. Any other questions? All right. If not, have a good weekend, and you should have your next homework tonight sometime, or this evening, and you'll have till the Tuesday before your second midterm. So that's when the homework will be due, after next week, essentially, after I cover the material for next week. But most likely, all you'll need to do the homework is what I cover on Tuesday, not so much what I cover on Thursday next week. So you should be able to get started on most of it soon. You could at least do the first 3 or 4 questions before I do the material for next week. So next week, we'll talk about subgradient methods. Okay, we'll first define what a subgradient is. And then your midterm will cover basically all the material through the end of next week. So next Tuesday I'm sorry, the Tuesday after next will the day before your midterm, when homework 5 is due, we'll also have a review session, just like we did for the first midterm. And hopefully, I don't think I'll have your graded homework 5. I don't think the TAs will be able to grade homework 5 in time to give it back to you before the midterm. but I thought you guys will need more time. That's why I didn't make it due next week. But you should have the solutions that you can just double check your own solutions before the midterm. And as far as the midterm, I should say one more thing about the midterm. I'm going to make it open notes, open. So since nobody told me that they couldn't type. So, but you can't see the notes on your computer, but you have to have a hard copy of the notes on your desk. Okay. So nobody complained that they couldn't print my handwritten notes. So I'm assuming you're all okay with that. So you can have that, and you can also have the solutions to your homework problems that you wrote up. You can have all of that. Any hard copy stuff you can have on your desk when you take the exam. Okay. All right. Okay. See you next week.
See you next week.